Our next talk, which will be given by Pratik Nandy from Indian Institute of Science, Bangalore. And I ask Pratik to join.
Yes, I'm here.
So share your slide.
Is it visible? Hello?
Yeah,
Yes, it is visible.
Okay.
Okay, so you have like roughly 20 minutes, so keep that in mind. So let's start with Pratik's talk. So he will talk about renormalized circuit complexity. So Pratik, please start.
Okay, so thanks. So I'll be going to talk about our recent paper on renormalized circuit complexity. So it's based on his paper with Arpan and Anindya. So the plan of the talk is to first introduce the complexity. Already Shira has been introduced this complexity, but I'll more elaborate on this Nielsen's gate counting, and we'll see there is some drawbacks of this Nielsen gate counting that will be improved by invoking this Suzuki-Trotter algorithm, and this by this algorithm we'll see this is connected to this holography using this path integral optimization, and we'll conclude after this section. So as Shira have already talked, this complexity is minimum number of quantum gates required to build an unitary operator. So there are basically two kinds of complexity. So one is a set complexity and another one is unitary complexity. So I will be mostly talking about the unitary complexity, but we want to build a unitary operator. So the minimum number of quantum gates is required to build this unitary operator is defined as the complexity. So in general, the problem is a hard problem. So the Nielsen and these collaborators want to geometrize the problem such a way the minimum number of gates is required. A geodesic length between this identity operator whose complexity is 0 and the desired unitary operator that we want to find. So this is given. So this means that we want to parameterize this geometry actually has a useful thing. So because this allows us to use the tools of Riemannian geometry, and for that we need to parameterize this path by a s such that this for s equal to 0, this is we have the identity operator that we start, and for s equals to 1, this is our desired unitary operator. So the actual procedure of Nielsen involves 3 steps. The first step is to define a control Hamiltonian and break it into easy and hard parts. So this is the part contributes from easy part, and this is just a hard part. This OI just does just 2 qubit or multi-qubit gates. For easy part, it's just a single and 2 qubit gates, and this for the hard part, this could be a more than 2 qubit gates, which are hard to build. This YI is just control function, and this just give a weightage to these operators. So the idea of Nielsen is to penalize these hard gates by introducing some penalty factor. So the total cost is given by the total. We can define a cost functional which depends on this yi, and the total cost is given by the total length of the curve, which is some function of this yi. And the idea of Nielsen is to introduce a penalty factor and to penalize these hard gates such that, and define a projected Hamiltonian by completely deleting these hard gates. So this will introduce some error in your problem. So the next step is to define this. We have a geodesic distance d, and we want to divide this geodesic distance into n steps with equal interval delta, and for each interval you are going to define an average Hamiltonian by this formula, and with the average unitary by this. So, and this is for this formula is we are going to apply by n times because we have divided it into n steps. So this is advantageous because in projected Hamiltonian you have something dependent on S, but in the average Hamiltonian this is just a constant Hamiltonian. It's averaged. So this is bypasses the path order expressions. And the final step is to divide this 0 to delta interval into R steps and approximate this interval is in terms of unitary quantum gates. So Nielsen uses this Lee-Trotter formula, and the total number of gates actually goes as some kind of m square dq and delta square by delta square. So m is the number of easy terms in the geometrically local Hamiltonian. So and this delta is just specified tolerance. So this geometrically local Hamiltonian is important because for geometrically local Hamiltonian, as shown by the Preskill, is a proportional to V. By definition, it is proportional to V, and this scales as V square. So this the naive gate counting by the Nielsen is actually goes as a volume square. Is not the volume, but as Shira has already talked, this complexity is it should grow like a volume law scaling. So this is not the correct way, or I mean not the optimum way for this gate counting. So we'll so the last step actually we can improve the last step by using the Suzuki-Trotter method, where this is the average unitary operator, and we want to approximate using this S operators by the Suzuki-Trotter higher order integrators of Suzuki-Trotter method. Whether we start from a basic sum S2 by given by given by this formula, and we by recursively we can build for higher order S2k by using this formula, and this will give us some error like this. And if we invoke this Suzuki-Trotter formula, we can. So okay, so actually let me explain this formula, because this is just two kind of arguments, is 1 minus 4 over k, and this is just qk. So this is a total 5 terms. So we can represent this recursive relation in terms of a network structure. So this where we start from something k equals to in S2, and this is just S2 circuit. This is S4. This is S6. So as we go along, this is in the k direction. This increases in the k direction. So this is just a formula for we start from S2 on the center, and this according to this formula, this k increases, and there's 5 legs because we have total together 5 terms, and this color differences because there are some the difference between these arguments. So this is the pictorial representation of the Suzuki-Trotter circuit, where this is just a coarser circuit, and this is a more finer circuit. So this error in the circuit pictorially, the error in the circuit is actually very less, and this interior is we have a more error. So if we use the Suzuki-Trotter formula, so we get the total number of gates is something scales like something like this, which depends on the scale, the order of Suzuki-Trotter, and where this has some scaling, so 1 plus 1 over 2k. So we see this when k tends to infinity, so this actually dependence becomes a linear. The number of gates which we define as a complexity becomes a linear. But there is also a problem, because this factor also blows up. So there is a competition between the two factors, this factor and these factors. So if you plot this total number of gates, we see a minimum where this minimum of this plot. So we want to optimize this total number of gates by this k factor. So to remind us, this formula actually Preskill also got some similar kind of formula, but he used a different exponential rather than 5 to the power 2k. But Preskill also got this 1 plus 1 over 2k formula. So the optimization actually comes from the Barry's paper, where they optimize with respect to k, and then the total number of gates actually is a linear function of spatial volume, if we think this k opt as an independent variable. So this is our specified tolerance. So we have some specified tolerance, so we can find the k optimal, and similarly we can find the total number of gates. So this omega dependence is now manifestly linear for a fixed k optimal, as suggested by the holographic proposal. This is just a volume law scaling. But there is also a problem. So if we change delta to 0, this total number of gates also becomes infinite. This is rather trivial, because if you want to arbitrarily approximate some unitary arbitrarily close to the actual unitary, the number of gates should be become infinite. And there is okay. So there is also uh, uh, a problem for them from the experimentalist point of view. Suppose we have some given some delta, given some two different delta. So the two different delta, we have a two different total number of gates. So each time we have a different tolerance, given different tolerance, we have different number of gates. So from an experimentalist point of view, this is a complete disaster, because each time he or she has to build a different circuit with a different number of gates. So the best thing, what could be better for him or her, is that if a total number of gates become independent of the tolerance, whichever tolerance which I will give, while I will use that same number of gates. That means this number of total optimal number of gates should be independent on this tolerance. That means should be independent upon this k optimal. So the way we can demand this k optimal is independent of this k optimal. So that means this if we differentiate this with respect to k optimal, so we'll see this this leads to this equation. There's a d. In fact, what previously taking as a constant is actually a function of this k optimal. So a simple solution is just a exponential function of d, and this will lead to a constant total number of gates. But but in general, d is also dependent on the penalty factor, because we in the manifold we have also penalized some gates, and we get the geodesic distance. So there must be a complicated relationship between this geodesic distance and this penalty factors. So we a priori we don't know what is the relation. So it can be very hard. So it can be very hard to solve this solution for an arbitrary relationship between d and p. But what you can do, we can choose for a large p. We can see this d actually can be which goes proportional to the p to the power alpha, where we can consider two logical possibilities. One is for alpha greater than 0, and one is for alpha less than equal to 0. So if we define some effective coupling, some sense of g equals 1 over log p, and k optimal is some log of lambda. This lambda 0 is some reference scale. We can see the equation. This looks like similar kind of beta function equation that we can see in QFT. So the beta function equation can be, this beta function can be positive, or we call it a flow function. It can be positive or be or negative, depends upon the choice of this sign of this alpha. For alpha equal to 0, this is just increasing function with k optimal, and this for alpha less than 0, it is just a reverse thing. We can plot this coupling with this lambda, and we can see this is two plots. This is one is just increasing, and decreasing is like QED and QCD in context of similar kind of what we came across in QFT. So we have used this. We got this plot by using this Suzuki-Trotter formula, but the actual the Suzuki-Trotter scheme is not a vital scheme. In fact, if this was a growth of some e to the power lambda k, so this right hand side of equation, this actually replaced by some minus 2 gamma. So actually this so it means the algorithm, the Suzuki-Trotter scheme is not a vital, but we need just exponential growth, and this becomes an universal result. And the dependence of, because this is just a linear function of omega, so we can think this as a the density of gates. So as kind of density of gates, and we want to find what is the holographic interpretation by this density of gates. In the next section, we will see this can be achieved by using this path integral optimization method developed by Tadashi and other people. So the path integral complexity is developed by Tadashi and other people, which is basically optimization in this minimization of certain functional with respect to some background metric. And then in 2D CFT, it is well known, this is given by the Louisville action. So this is the Liouville action. So this Z is the Euclidean time, and it's the spatial coordinate, and this is the potential term, and this is some kinetic term, and and this is the central charge. So we want to penalize. Now we want to penalize this Liouville action. So we want to penalize this derivative direction. So we say that derivative direction is harder directions than the potential direction. So we want to penalize some penalty factor, and this penalty factor is actually dependent on this tolerance that we have previously said. So in the discrete case, so in the continuum case, you also demand this is kind of it depends on this tolerance. So we can extremize this action, and we get the equation of motion, and the solution is a pretty simple solution, and with the boundary condition is given by this z equals epsilon, where we have created the state, vacuum state. So on the solution, we can evaluate the Liouville action. So this, which is given by just a p square over epsilon, and this is as according to this path integral optimization picture, this is just a total number of gates. This action, which can also be given some interpretation in terms of tensor networks also. So this is the total number of gates, and we want that also to be independent on this given tolerance that we previously said. The total number of gates should be independent of tolerance for an experimentalist point of view. So this is also we differentiate with respect to epsilon, and we set to 0. This gives a pretty simple solution. It's just proportional to epsilon. In this case also, we can define an effective coupling G and some RG scale lambda, and we get also some kind of a beta function equations, which is just now this is just a positive flow function equation because the sign is also already positive. So to find an holographic interpretation of this density of gates that we have said, so we first calculate the on-shell Lagrangian density, which is given, which is just calculated given by this p square by epsilon square from this action, and on the extremation condition, which is we can evaluate this is just given by 1 over epsilon. So this on this extremation condition, this is just a monotonic function, and as you know, this the action is just interpreted as the total number of gates. So the Lagrangian density is identified with the density of gates. So we want to find this, what is the holographic interpretation of this? Is a kind of monotonic function, so we want to have the holographic interpretation of this. So this is well known. This is an RG flow of a metric in d dimensions can be written in like this, where for a fixed point in this metric just reduces to ADS metric. For a 2D CFT is just exponential 2 of the CFT things, and we can get an H2 slice by defining by 1 over z square. So this becomes just 2 over z square by this formula. So on the fixed point and on the solution, we can identify this exponential of 2r is just 1 over z square. So without the penalty factor, we have the precise identification that this flow function is just 1 over epsilon square. So we propose the same thing. This can be identified even introducing this penalty factor. If this exponential of this monotonic function a to this penalty factor, so that can be related to this on-shell Lagrangian density. So as this both are the monotonic, so that can be related. So in this way, we can say this density of gates is related to this geometric RG flow function A, and this monotonicity is related to the monotonicity of this AR. So we can have an holographic interpretations of this density of gates in via these equations. So what is the main message of this thing? So the main message is this: the naive counting of the Nielsen is proportional to the B square, which is a kind of naive gate counting. But using the Suzuki-Trotter, we can count the total number of gates, which is just proportional to this volume as required by the holography. And it can be also shown there is no algorithm which can lead to the sublinear scaling in V. So in kind of sense, this scaling is optimal. So we can have a naive gate, we can have an explicit gate counting, which the result actually matches with the holography calculation. So the main message is, suppose we have two different techniques, ADS safety and this quantum computers, we want to see which one is the best. This technique reveals actually the best quantum computer actually somehow this reinvents the rule of the ADS-CFT. So the best quantum computer works in the rule actually somehow follows the rules what the ADS-CFT does. So I think this is the end. So thank you.
So thanks, Pratik, for the wonderful talk, and we can take some questions if you have for Pratik. So you can ask him directly.
Maybe I can ask.
Yes,
Yeah.
sure.
Can you explain if there is a relation between your definition of complexity and the count of gates in Mera tensor networks?
For in the context of this path integral optimization, it can represent this path integral in terms of the tensor networks, right? So and in that case, for we can actually count this because we have tensor networks in total space volume. So this is so the metric actually is just the total number of gates. This is just a volume contribution in the tensor network parts, and for each if we consider each tensor network each tensor takes some volume, and we want to interpret this each tensor as kind of gates. So, and these two terms actually represent this is the uniformity of this the field that in the both x and z directions. If we have some tensor networks, we have some TNL algorithm. You just have an constant jump over two layers of the tensors. So that means this kinetic terms only depend. I mean, there is some terms which only depends on the derivative of this phi, because phi jumps in the tensor networks in each step. So there is some derivative term that should be in the total counting of total number of gates that we can call it the kinetic term. So this z and x because we can have uniformity in the tensor networks in the direction. The square is because you can go tensors, you can shift your phi from the lower to upper or upper to lower. It doesn't make any changes. So this is a volume term in the tensor network picture. This is also can be represented as some kind of surface term. I mean some term which is not the volume term. So this is some kind of surface term, some kinetic term. So does that answer your question?
Yes, thank you.
So any more questions? Okay, so if not, we thank Pratik again for the talk.